Okay, so I'd first like to thank the organizers for inviting me to come and give this talk, albeit virtually. It feels a little bit strange giving this talk by recording it because I feel like I'm just talking to myself. But in any event, I look forward to speaking with you and meeting you over Zoom when I'm giving my presentation. So today I want to talk about the question of how the brain allocates control over different strategies for solving a problem. And I think that I'd like to kind of illustrate this, if I can actually get the pointer to work. I'd like to illustrate this with respect to something I've been watching a lot of during the lockdowns, which is home improvement shows, or specifically house building shows. And as anybody who has ever watched one of these TV shows about building houses will know, is that every good house build has to have a project manager. Okay, so you have to have somebody who is allocating control over all of the different jobs that are done on the on site, and basically nominating different subcontractors to go and do particular jobs at particular times. And if you don't have a project manager, it usually decays into chaos. Okay, so obviously, if you will have different jobs like a plumber, electrician, carpenter, and roofer, and so on, and the project manager basically has to decide based on what he or she wants to do at a particular moment of time, which these experts to nominate. So you have kind of electricals need to be done, well then clearly you need to kind of nominate the electrician, okay, at that particular moment in time, okay? So what I'm interested in is, to what extent does this analogy apply to how the brain might work? Because of course we can think of the brain as being composed of different expert systems, different subsystems that have, evolved to do different things, and that they have different information, they act differently, they operate differently on that information. And based on what's happening in the world, different experts might be useful at different moments in time. So the question is, can we kind of understand a general framework for how this might operate? And it turns out that there is an idea in machine learning that you could have different expert systems, which are basically, different modules or different neural networks or what have you, different subsystems that basically are operating on different aspects of a problem or solving a problem in a different way. And then you could have a manager that basically allocates control over these and or allocates weights essentially over which of these systems should have access to behavior. And so by analogy to the brain, you could imagine that there are different expert systems. I'm just kind of showing, 4 arbitrary ones here, and that these systems are going around sampling from the world as the agent is doing things and making predictions, perhaps suggesting particular actions that should be taken. And the manager can observe those predictions and can also observe what the outcome has been of those predictions, and then can make a judgment about which of these experts is actually making the most reliable prediction at any one moment in time, and then allocate weights over these experts proportional to their reliability. It doesn't have to be all or nothing. It could be that several experts get selected and weighted in different ways. And the idea is that the kind of by integrating over these experts, you can actually select behaviors that are better than if you just were to have a single expert or even just nominate one at a time. Okay, so you kind of get the benefit of the knowledge of the crowd of experts tailored to a particular point in time. Okay, and so what I want to do is spend a bit of time discussing where these ideas emerged from, and maybe giving some examples of expert systems that in which we can actually test this hypothesis that there's this kind of reliability-based arbitration going on between experts. And so where this idea, first originated, at least in terms of the decision neuroscience literature, came from the work of Daw, Diane, Yale Niv, and others. And they've suggested that when it comes to thinking about systems for controlling action selection, learning about the world and selecting actions on the basis of what's being learned, you can consider there to be two different kinds of reinforcement learning, so-called model-free and model-based. And model-free is presumed to basically take actions based on what actions were rewarded in the past. And this is kind of presumed to be analogous to the construct of a habit in behavioral neuroscience and behavioral psychology, which is this kind of action that gets selected because it worked well in the past, but doesn't really consider the current context or situation. So sometimes a habit can be maladaptive if it kind of persists in a situation where it's no longer appropriate. And model-free RL also has that quality. It just basically selects actions based on past reward. This can be contrasted with model-based reinforcement learning, which is more deliberative. It involves planning and involves an internal model of the world, an internal representation. And using that internal representation, let's say of this kind of house, you could then compute by planning over the internal model what actions you should take. So if I put a reward here, you could then choose the route through which you would navigate yourself in order to get to the reward, okay? And so these two forms of reinforcement learning are proposed to account for more goal directive or deliberative planning-based decision-making versus more kind of reflexive automatic decision-making, respectively. And these systems have been studied using kind of certain classes of tasks called multi-step decision problems, Markov decision problems. And in these tasks, basically, you imagine that you are in different states, which are denoted by these fractals. So this fractal here has two possible actions that you could take, left or right. So a participant might be playing this task, they'll see a fractal, and they can choose to go left or right. And then they transition to different subsequent states, which then are subsequently transitioned to other states by taking further actions. Okay, so this is kind of this multi-sequential problem. And the idea is that you can use this problem to study both model-based and model-free control. So the idea in the kind of model-based system is that it would learn about all of these different transitions. So how can you get from here to here, for example, by taking which actions should you take that gives you the highest probability of transitioning. So these are transition probabilities here, I should say. And at the end, one of these states or several of these states give you a reward. So for example, here you could win 25 cents if you get to this state, whereas other states are not going to be rewarding. So for example, this one gives you 0. So you're kind of motivated to take the actions that gets you to the states that give you the highest reward, okay? And so, as I said, a model-based system will basically encode these transitions between states. Then you can, if you have that knowledge, you can then plan which action to take in order to get to the high rewarding state. But a model-free system just learns to take actions based on past reinforcement. Okay, and I'll kind of explain how that's proposed to work now, very briefly. So model-free reinforcement learning goes back a long way and goes back to early psychological models of learning. And the idea is that learning proceeds by virtue of prediction errors, which basically signal the difference between expected reward and the actual reward R that's received. So expected reward V and the reward R that's received. And then you update your expectation proportional to that prediction error, and then choose the thing out of the possible set of actions. Let's say you have actions A, B, and C. You choose whichever action gives you the most reward. Okay, and so just imagine here that you're in this state denoted by this fractal. You have a low expectation V of reward, and then suddenly you get a reward, and then you'll get this positive prediction error. Okay. And so I'm sure many of you are familiar with this notion of prediction error, so I won't belabor the point. But the point being that you can get kind of both positive prediction errors if it's an unexpected reward, and you can also get negative prediction errors if kind of, let's say, a reward is omitted unexpectedly. And the reason people got really interested in this prediction error idea is based on work from originally by Wolfram Schultz, in which he recorded from dopamine neurons and found that there are these phasic activity patterns within dopamine neurons that seems to act like this prediction error. And I think that arguably gave rise to much of the field of neuroeconomics, in which it started to become clear that we could find evidence for learning signals that underpin economic or value-based decision-making in the brain. And so that's maybe the idea about how model-free systems learn via reward prediction errors. And conversely, a related idea is that a way in which a model-based system could learn the model of the world is by making use of a thing called a state prediction error. So a state prediction error is distinct from a reward prediction error because it is about learning about the transition probabilities between states. So learning about what states you should expect to end up in as a function of taking particular actions, as opposed to just learning about what rewards you get for taking particular actions. So again, if you imagine that you are in this state, starting here, and you expect to end up here, well, then you'd have, let's say, a relatively low state prediction error because you're not expecting, you ended up where you expected to end up. But if you end up in this other state, surprisingly, well, then you'd end up with this big positive prediction error. Okay, so you can look for these state prediction errors and reward prediction errors. And in previous work with Jan Glacier in collaboration with Nathaniel Dahl and Peter Dayan, we looked for these signals in the brain. And this is a very classic result that we found by myself and others for many years, is that you'll see these prediction error signals, reward prediction error signals in the brain, especially in places like the ventral striatum, which are kind of receive these rich dopaminergic innervations. But you also even can see them if you look using high resolution fMRI, you can see them in the midbrain in the dopaminergic nuclei as well. So we can see evidence in humans, not only in monkeys and mice for these kinds of reward prediction error signals, but also we can look for state prediction errors, and we actually see those too in the brain. Okay, so this shows you actually a frontoparietal network correlating with these state prediction errors. Okay, so it suggests that there are both of these two learning signals are present in the human brain, these state prediction errors for potentially learning a model, and the reward prediction errors for learning these action values in the model-free system. And so one question that we're interested in, which is kind of building on an initial theoretical idea by Nathaniel and Peter and Yale, is imagine that you want to understand how these two systems compete to control behavior. Okay, so imagine that there is some way of allocating control over these two systems or arbitrating between them as a function of which system is best suited for controlling behavior at any one moment in time. And so what the original idea that was proposed is that you might rely on the uncertainty in the predictions of the two systems. Okay, so you basically favor the system that has the least uncertain prediction at any one moment in time. And so we wanted to kind of build on that, but we wanted to think about a heuristic, and this is work with Sangwan Lee and Shin Shimojo, is a heuristic for how you might learn these predictions about how reliable the systems are. So you're not talking about learning the predictions within the systems, you're talking about learning about the reliability of these predictions. And it turns out that one thing you can do, it's kind of a cheap heuristic, is to track the prediction errors that are accumulated in the two systems. So in the model-free system, if you're getting a lot of reward prediction errors, that probably means that your model-free prediction is less reliable, right? As compared to a situation where you're getting few reward prediction errors. And similarly, if your model-based system is accumulating a lot of state prediction errors, it probably means that you have a bad model of the world compared to when you have few state prediction errors. And the idea is that you can, by keeping track of these prediction errors, you can compute an estimate of the reliability, which is based on the average amount of accumulated prediction errors in the two systems, and then use that to allocate control over these two systems, so that behavior is a mix of these two, model-based and model-free. It doesn't have to be actually all or none, it can be a mix of both. And so one question is, well, can we actually test this hypothesis that the reward prediction errors and state prediction errors influence the degree to which behavior is model-based and model-free? And what I'm actually going to show you is more recent work that we've been doing over the course of the pandemic that we think provides kind of more kind of cleaner evidence for this story. And then I want to kind of go to other systems, other potential experts, and see to what extent does this framework generalize to those. And if we have time, I'll hope to be able to show some of this, of what's going on in the brain too. Okay, so how can we study this arbitration process between model-based and model-free experimentally? And so it turns out there's a kind of a class of this MDP problem that's become very popular in the literature. It's called typically called the two-step task, in which there's a specific manipulation that allows you to separate model-based and model-free. So the basic task is very similar to what I've already just shown you, except here, actually, in this version, it's kind of, we're dressing it up as a spaceship task or space task in which you have to choose between two spaceships. You can then end up landing on one of two planets, and then within those planets, you can end up either of one of two landing places, okay, per planet. And so these are kind of, you make choices and you transition. Again, you have common and rare transitions and so on. And so that's kind of the way that the task looks. The versions of these tasks that have been run in the literature have allowed you to separate out model-based and model-free strategies in general. And the way it's worked is that it depends on what happens after you end up taking a rare transition. Okay, so imagine here that you choose this spaceship, and this should get you here 70% of the time. Okay, so that's a kind of the common thing that happens. You'll end up on the red planet, but every now and then, 30% of the time, in this case, you'll end up on the green planet. Okay, so if that happens and you get a reward, then the question is, what do you do on the next trial? And so according to the model-based system, if you take this rare transition and you get a reward, actually the right thing to do is to choose the blue ship next time, because that's actually going to get you to this planet more likely, right? On the next time, because you know that this is a higher probability of getting to this planet by choosing blue. So that's what the model-based system would do, but the model-free system would actually be more likely to choose the option associated with the rarer transition next time, because it basically doesn't care about the model, the relationship between these things. It just cares about what gave it reward in the past. Okay, so it'll basically take the action that gave reward in the past, which is to take this option here. Okay. So what you can look at is what's the probability after this rare transition that you stay taking the same action or you switch actions, okay? And so Daw and colleagues have kind of separated out the pattern of behavior, what that would look like if you were kind of a purely model-free, it's called reinforcement here in their paper, a purely model-free agent wouldn't care. There'd be no difference between common and rare transitions. They just increase the probability of taking the action that they took last time. Whereas in a model-based system, it would be more likely to switch away after a rare transition that was rewarded compared to a common transition that was rewarded. And you kind of see a mirror image on the other side for unrewarded actions. But basically that's what behavior looks like, and this is on their original task. It's a mix of the two, okay? But we wanted to take that task and we wanted to add extra manipulations to it. So we wanted to sort of manipulate the reward prediction errors, so that at certain periods of time, there are greater reward prediction errors. In other periods of time, there are lesser reward prediction errors. And the way we did this was basically manipulating the reward magnitude and the probability of winning. And so over the course of the experiment, we could basically get blocks of times when there's high reward prediction errors and blocks of times when there's low reward prediction errors. Okay. And we could also manipulate the transitions between states, which is, remember that if you have these state prediction errors, you're going to have low state prediction errors if you end up being in a reliable model in which there are reliable state transitions. So for example, here, 90% of the time you end up here, and only 10% of the time you end up here. So that's kind of pretty reliable world in which most of the time you know where you're going to end up. So you're going to have low state prediction errors. Whereas in this kind of more uncertain world, you just have a 50-50 chance of landing in either of these two places. Okay, so that's kind of introducing these more unreliable state transitions. So we can also manipulate that in the task across blocks. Just to show you that we ran this actually in 2 cohorts that I'm going to talk about today. We ran it online in MTurk. Again, this is actually, this was planned before COVID hit. We were planning to do this kind of big online study, so it's kind of fortunate that we had planned to do that, because that was the only thing we could do for a good period of time during the pandemic. So we were able to run this study in a large cohort online, have them do the task in which we're manipulating these variables. And we also were able to do it in which we had originally planned to bring people into the lab and test them, but we couldn't do that physically because we were not allowed to do human subjects testing during various periods of time in the pandemic. But what we could do is we could have people take the task at home, but in which we know who they are. So we have their information, they're real participants, they're not bots. And we track their performance and explain the task. And basically, it's almost like the next best thing to doing it actually physically in the lab, but they're doing it on their laptops at home. Okay, so we had these 2 groups, and this just shows you that they show the standard kind of behavior that you see, in which behavior is a mix of model-based and model-free. But what we then wanted to do is manipulate the, as I said, the reward prediction error and the state prediction error. And we actually have another manipulation too, I'm not going to talk about today. But the bottom line is, I don't want to spend too much time going through this data in detail, given the time constraints, but is that if we manipulate reward prediction error and we look at basically the difference between the state probabilities for rare versus common, okay? So remember, model-free, there should be less difference between rare and common. And for model-based, there should be more difference. And if we induce high reward prediction errors, basically behavior looks more model-based. It's still pretty model-based here in the lower prediction error condition, but you're basically making it more model-based. And that's kind of also showing this here, what this is, as a function of high reward reliability, behavior looks more model-free. So this is kind of the high reward reliability condition here, because you have low RPEs. So that's what this is showing. So this is kind of an easier way to envisage this effect. But also we can see that the state prediction error manipulation works too. So again, if you are in a situation of low state prediction error, prediction is you should be more model-based because you have a more reliable model of the world. And that's also, oops, I'm so sorry, what happened there? That's also what happens, okay, that you see this kind of more model-based control as envisaged here. So you get basically more model-based when state reliability is higher, okay? So this is another replication in the in-lab data, and I'm not going to go through it, but the effect is there, albeit slightly less robustly, but we have a very small number of subjects, relatively speaking. Okay, so what we can show so far is that we could push behavior around to be either more or less model-based as a function of inducing changes in the reward reliability, in the model-free reliability, and in the model-based reliability by manipulating these prediction errors, which fits with the theory, this reliability-based theory of arbitration. Okay. So the next thing that Carolyn Carpentier in my lab and myself were interested in is seeing whether we could extend this idea of this kind of reliability-based arbitration notion to other types of expert systems that might be involved in facilitating learning and decision-making in humans and in other animals. And one type of system we kind of decided would be interesting to look at is observational learning, right? So the systems we've talked about up to now are what we call experiential learning systems, where you learn to make predictions on the basis of the experience that you get by interacting with the environment directly, right, and receiving rewards or not, as the case may be. But in observational learning, you get to learn by observing other people, right? Other agents act in the world. And you can if you can exploit that information, then you can use that to also guide your own choices. And of course, that's clearly very advantageous because we need to learn lots of things through observation and by observing others, other conspecifics. And it also helps us to avoid consequences that might befall the other person, which could be adverse, right? So if you watch another person falling down a hole, well, you can obviously avoid that by not taking the same actions as that other person. So it clearly has a lot of advantages from an evolutionary perspective to learn to, through observation, and avoid taking actions that lead to dangerous outcomes that you observe other people experiencing, or vice versa. I mean, I'm guessing that some aspects of observational learning have not necessarily worked during the pandemic in certain behaviors, but that's something to discuss maybe at another time. The idea is that we can actually differentiate between different forms of observational learning. So one form of observational learning is called imitation, right? So let's say you are observing somebody play darts, okay, and you could just imitate their behavior. I'm going to imitate what they're doing, okay? And that's perfectly fine. It can be a reasonable strategy, of course, so long as the person who you're imitating is actually doing well and is someone that you trust, right? There are going to be conditions under which imitation is going to make sense. But conversely, the other thing that an agent could do is actually try to do a thing called emulation, okay? And so emulation is the idea that you're not just copying the agent, you're actually inferring something about the goals that they're pursuing, right? And so, for example, if you learn that the person is trying to hit the bullseye of the dartboard, well, then you've learned something about their goal, and that's actually useful information for you if you end up having to throw darts, right? You learn, well, maybe I should aim at the bullseye. Right? So these two strategies can be very useful under different conditions. And then the question is, does the brain actually arbitrate between them in the same way as it does between model-based and model-free control? And so Carolyn Carpentier developed a task that would allow us to do this, also in collaboration with Kyo Igaya. And Kyo is new faculty at Columbia. I was very sad to lose him from my lab, but he's a great computational neuroscientist and will be a wonderful collaborator. So my loss is your gain. So in any event, the task is kind of involves a kind of bandit problem in which you see other agents choosing from these bandits. And what the agent is doing, the other agent is doing, is working to get tokens, okay? These green tokens, blue tokens, and red tokens. And you as the observer see the agent making choices, but you don't know what the value is of these tokens. Instead, the agent knows that you're observing, but you're not privy to that information. And the thing is, you also get to choose from these slot machines from time to time. So you are incentivized to try and understand what action is the agent or what token is the agent working for, okay? So if you're using an emulation strategy, you're going to try and infer what token is the agent working for. But also, if you're just doing imitation, you're just going to copy the action that they took, okay? So in any event, what happens is that when you see the slot machines, you actually see that the color of the slot machine reflects the probability that a particular token will be delivered. So this one will give you green with a high probability. You'll get red with slightly less, and very low probability of getting blue, and similar vice versa for this one, right? So a different setup. Okay, so every one of these slot machines in a given block has specific reward probabilities associated with it. And so if you're going to do emulation, if I see a person choosing green, maybe I can infer that this person is working for the green token, okay? Right? But of course, it's possible that the person's also working for the blue token, right? So there's some uncertainty. So I have to kind of maybe integrate over history in order to try and kind of work out what token is this person actually pursuing, okay? Whereas conversely, excuse me, conversely, via imitation learning, I'm just going to copy whatever that person did. So what we're interested in is trying to understand which of these systems is the person deploying, and also can we manipulate the reliability of the systems in order to change the allocation of control. So what we did was manipulate the reliability of the two strategies. And it was done very simply in the, for the emulation system by basically just changing the relative probabilities that you will get a particular token for choosing a particular slot machine. So here you can see it's fairly easy to see that if the person chooses this one, they're likely going for the the blue slot machine, or they could be going for the green one, right? And here they're more likely to be going for the red one, right? So you can sort of tell based on the choices that there's a certain probability that they're going for one or other of these, that they have in mind one or other of these tokens. And over time, the tokens change, the relevant tokens change. Whereas in this high uncertainty condition, basically what happens is that it's just much harder to solve it because there's much more uncertainty over which token they're working for as a function of what they choose. Okay, so we're manipulating the uncertainty. Another manipulation we had was which worked, I think, less well, actually empirically, was to manipulate the action volatility. So here we're changing the token over time as to which one is the agent is currently working for. And in the high volatility condition, we basically switch the token very frequently. And the idea there is that you'll then have a lot of volatility in the action selection. So imitation will be very uncertain, whereas you'll have much lower uncertainty when you're in this more stable condition. Okay, so we're kind of doing these manipulations. And then Carolyn fit a computational model that is basically doing arbitration over the two strategies of whether you use an emulation or imitation strategy as a function of how reliable are the predictions within the two systems, okay? So she calculated emulation reliability by calculating the negative entropy over the emulation action values. So you'll basically be more reliable if you have less entropy. Or emulation reliability was basically by tracking the prediction errors for choosing actions, okay? Now, it turns out that imitation reliability is not playing a big role in this task, so far as we can tell. It's mostly emulation reliability. So in any event, we could then compare different models, including an arbitration model, or just these two strategies by themselves. And the arbitration model, a reliability-based arbitration model, basically explains the data better than does these other two strategies. And that's kind of replicated across two separate studies. And then we can look at behavior, and I'm not going to belabor the point too much, but essentially you can show that as a function of reliability, behavior is more emulation based when you have low entropy, low uncertainty, and it's more imitation based when you have high entropy, high uncertainty, okay? This is just showing you the relative likelihood of the two models estimated as a function of these different conditions, okay? And this just shows you that the arbitration weight is higher under the condition where you have low uncertainty, and lower under conditions where you have high uncertainty in the token observation, which is what we think is being used for the emulation system. Okay, so that's kind of suggesting that we have a similar framework. I'm going to kind of get to kind of brain data later, maybe in the last few minutes of the talk, because I'm kind of running kind of already towards the limit in terms of the time. But what I want to also kind of briefly cover is that we've tried to extend this idea further into the domain of the interaction between experiential and observational learning. So this is kind of other work that Carolyn's been doing actually during the pandemic, in which we haven't been able to collect in-person data. But what we're interested in is kind of developing a task in which you have both observational and experiential learning going on at the same time, and in which we can also manipulate the reliability of the observational learning strategy and the reliability of the experiential learning strategy. Okay, so basically the task is, you see these two options here. You observe another person making these choices. This person gets a token, okay, which could be kind of either blue or orange. And this person is working to get a particular token, and you don't know which token they're working for. So that's similar to the previous task, because one of those tokens is rewarded and another one is not at a particular moment in time. And we manipulate the reward probabilities, or sorry, the transition probabilities. So sometimes there's a clear, you can clearly infer which token they're working for based on what they get, and other times it's more ambiguous. And we can also manipulate, and then beyond that, you also get to make your own choices. You actually get to choose between the tokens. So you don't know what tokens are currently rewarded. Again, there's a probabilistic aspect to this, but we can manipulate the probability of getting a reward based on choosing a token, and that will change over time too. Okay, and we also vary that to have, you know, high uncertainty over which token is the best, or low uncertainty. Okay, and so the idea is that maybe there's an arbitration process which is a mix of the two strategies, and basically, we manipulate that over time, and we've fitted an arbitration model to this data. And I don't have a lot of time to go into the details, but essentially, if you do a hierarchical model fit in which you have this dynamic arbitration model as a way of trying to explain participants' behavior. So this was data collected on Prolific. It was about, I think, 200 and something participants. And we can then fit the dynamic model in which you're having this dynamic arbitration, which is changing the degree to which you use the observational or experiential strategies as a function of reliability. And what we're actually finding is that that strategy does pretty well in explaining behavior, explains a good portion of the participants. But actually other strategies, including degenerate strategies like just always kind of choose the left or choose a particular color or so on, they also explain behavior on the task to some degree, as does observational learning only, and as does kind of like a fixed arbitration where you're kind of always using the same weight over the two strategies. But in any event, we do see evidence for this kind of more dynamic arbitration as a subset of the participants. And that may well be also an artifact of the online task in which maybe some people are not doing the task at all, and other people are kind of not paying attention. Or it may be actually really interesting from a point of view of looking at individual differences. Maybe some people are more have a greater tendency to deploy a dynamic arbitration scheme. So we actually identified these different groups that are in which their behavior is best explained by a particular model. And actually, I'm just plotting here the data of behavior in these groups. And what we're looking at here, this is kind of just a measure of how much is their behavior consistent with observational learning versus experiential learning as a function of these different conditions. And so the basic takeaway is that if we manipulate uncertainty, we are, as we predicted, pushing, at least in the dynamic group, the dynamic arbitration group, but also to some extent in some of these other groups, we're pushing behavior more towards observational learning if we increase the uncertainty of the experiential system, and we're pushing it more towards experiential learning if we manipulate the uncertainty such that observational learning has high uncertainty. Okay, that's what you kind of see here. So essentially, we're pushing around behavior as we predicted as a function of the arbitration scheme. And that's even present even in those people that are best explained even just by OL by itself or just by fixed arbitration. So I think it's just a question of a degree to which they're showing the behavior, which is kind of being kind of favored in the model selection. Okay, so a last thing I want to do, and I'm going to kind of probably run out of time to go through the neural data, but maybe I'll kind of briefly explain it, is we also are interested in the extent to which we can pit two other strategies against each other. A kind of affordance strategy versus value-based decision-making, which is kind of encapsulating the strategies that we've already looked at in relation to experiential learning. So affordance, the notion of affordance goes back to Gibson in 1979, who proposed that in visual perception, that certain behaviors, certain actions are facilitated or suggested by objects that you encounter in the world. So they kind of have an affordance. An example would be this gas can has an affordance, right? Which is to pick it up, right? To grasp it or to clench it, okay? And so each of these different actions will have different objects will have different affordances. And one question is, to what extent do affordances interact with value-based decision-making? And so Sang-Yun designed a task in which we've identified different object affordances, that the most dominant affordance out of 3 possible actions, which is pinch, clench, or poke. For a given object that you see, let's say this toolbox, it'll have a particular affordance that is most likely favored by people. And we basically find that out by running an online test in which we get people to make ratings about what action they think is most appropriate. And then we put 19 people in the lab, and we tested them on basically a banded task in which you see a particular object, and then there's 3 possible actions that you can select to operate on that object, and then you get reward depending on which action you selected. And we manipulate situations such that in a congruent condition, the action that has the highest affordance, let's say clench, also has the highest reward probability. Whereas in another condition, the incongruent, the action that has the highest reward probability is actually not the action that has the highest affordance. So there's kind of like a conflict induced between the affordance and the action. And what we're interested in is, to what extent do these affordances impact upon the action selection as a function of the rewarded value. And what you can see is that people do learn over time. This is kind of average learning curves, but that there seems to be a clear bias induced by the affordance. So people tend to be more likely to choose the high affordance action. And that's what you can see here. So this is how many times they choose the correct action, as in the rewarded one. And you can see there's kind of like a bias towards choosing it in the high congruent condition. Relative to, so remember there's 3 possible actions, it's 1 of 3. So relative to the low congruent condition, which is kind of in orange here and red, whereas they're biased away from the high probability, from the high rewarded action. Okay, so there's basically an interaction between the affordance, which is biasing actions towards the high affordance action and away from the valued action. And actually that bias seems to persist across the session, okay, of like blocks of trials. Here's like across 20 trials. And so this just shows you this consistent bias towards the afforded action, in spite of the fact that the afforded action may not be the rewarded one, okay. So we can also fit this data with computational modeling. And what we've been able to show actually is that you can compare different strategies. This is work by Sang-Yun Yi. And it turns out that, you could imagine that this could be just a bias in action selection. So affordance is basically biasing your action towards the thing that has the highest affordance. Or it could be just biasing your value. So basically giving you a prior over the value that the thing that has the highest affordance has the highest value, okay, even if that's not true. But it turns out that if we compared various strategies and included in this a reliability-based arbitration strategy based on the reliability of the value-based learning system, it actually fits the behavior best. So it was actually an incidental finding. We weren't expecting to look at the arbitration here necessarily initially. We're just looking at the kind of bias between affordance and value, or the interaction between affordance and value. But it turns out that this system, this model actually seems to explain behavior better. So I'm going to conclude by saying that we have evidence for the existence of dynamic arbitration between different strategies or experts within experiential learning between model-based and model-free, and within observational learning between emulation and imitation, and even between experiential and OL directly, and also between other kinds of choice. So affordance and value learning. So I'm not really going to have time to go into the story about the brain because I've run out of time. But just to kind of briefly summarize what we found is that there appear to be a mixture of experts architecture that's implemented in the brain. in relation to the ventrolateral prefrontal cortex, which appears to contain the reliability signals. So that was true for experiential learning between model-based and model-free, but also in observational learning, we found a region of ventrolateral prefrontal cortex also containing the reliability of the emulation strategy. And so one hypothesis is that this prefrontal cortex region, especially in the VLPFC, possibly other areas of prefrontal cortex too, is acting as the manager over the mixture of experts, and it's kind of allocating control over other subsystems as a function of which strategy has the most reliable prediction. And the other result we found is that the VMPFC, ventromedial prefrontal cortex, contains value signals, which are basically a mix of the two strategies, a weighted mix of the different strategies, whether it's between imitation and emulation, or whether it's between model-based and model-free. And so one possibility is that this framework within the prefrontal cortex, this region of these areas of prefrontal cortex are operating this kind of mixture of experts framework, recruiting different subsystems as a function of which system is deemed to have the most reliable prediction at any one moment in time. And one hypothesis is that it's doing this via kind of an inhibitory control. So inhibiting the system that is the least reliable at any one moment in time. I was going to talk about some direct current stimulation data that might support this hypothesis, but I guess I can talk about this if anybody has any questions during the Q&A. And I've already realized that I've gone over, I'm at kind of 46 minutes, so I'll have to conclude just by thanking all of the people in my lab who've been doing this work, especially those who've been affected by the pandemic in terms of just not being able to do human subjects work, or especially in person in lab work, especially brain imaging in the last kind of 2 years. And of course, it's none of us, fortunately, have been seriously affected by the pandemic in terms of our health. So we're very lucky in that respect. But of course, it's tough not to be able to do the research in the way we'd like to. But other than that, I'd like to thank you all for your time, and I'm happy to take questions in the Q&A.